Oh, we're starting. Okay, cool. All right. So here's from 08. I figured I would do one more example just so that we can see these problems worked out in a couple of different ways. I'm going to use the way that I did most recently in class using both reactants and starting amounts. So I'm going to take these values and I'm just going to highlight the two amounts of reactants that we start with, right? We know that this is a limiting reactant problem when we have two amounts of things in the beginning. Now, I notice right away that I'm going to be working with grams here, right, which is mass. So it'd probably be in my best interest to figure out the molar masses of those kind of like right away, because I know I'm eventually going to need those. In this case, heptane, that is the C7H16 compound. Oxygen is O2, right? So getting the molar mass of those just so that we have in our back pocket, we know that that is 32 grams per mole, right? 2 oxygen added together. C7H16, I mean, that one I'm not going to quite do in my head because that's a whole thing. But let's see, 7 times 12.01 for the carbon, plus how many? 16 times 1.01 for the hydrogen, and we get 100.23, so 100.23 grams per mole. So at least we have 2 molar masses that we can use to go from mass to moles of those substances, or moles to mass if ever needed. Now, when we go through these limiting reactant problems, you need to figure out which one is going to run out first, right? It's no different than that example we talked about with the ice cream and this chocolate syrup and cherries to make a sundae, right? You're limited to the amount of sundaes you can make given a certain recipe based on how much of the starting stuff that you use or that you have to begin with. So we have 2 different amounts of substances up there. What I need to do is I need to figure out a product that I can analyze, and I can figure out how much of a certain product should 400 grams of heptane make, and then do the exact same thing for that same product, but use 700 grams of oxygen at the beginning. And what that's going to allow me to do is take 2 amounts of those items and compare those in the end. So in this case, we're actually given the substance that we are wanting to produce, which in this case is carbon dioxide. So this is the product that we are trying to get to. So let me color code these as well, just so that we're all on the same page. We'll make this one nice and vibrant there. So I want grams of carbon dioxide in the end. So these are going to be straight up mass to mass problems. I mean, we've done these a bunch up to this point. Yes, it's long, and yes, it takes a little while, but it's worth it because in this direction we are able to kind of kill it, a little bit quicker than we were before, going from both the reactants to the same product. So I'll start with grams of heptane just because it's the one that comes first. So we have 400 grams of heptane. We have that as yellow. And then we also have the other reactant, that's 700 grams of oxygen. All right, so those are our 2 reactants, our starting amounts. And what we're going to do is we're going to compare how much of the product, in this case carbon dioxide, we can make. Because we are going from grams to grams, we first need to use those molar masses. Good thing we already calculated those, so we just plug them in. There are that many grams of C7H16 for every 1 mole. And then our next step would be crossing the mole bridge to go from moles of A to moles of B. I use the balanced equation to do that. For every 1 mole of C7H16 I have, there are 7 moles of CO2, right? We're going to that product, and that 7 comes from right there. Right, and the last step, the carbon dioxide, 1 C and 2 O's. The molar mass of that would be 44.01 grams. All right, and we are golden for that setup there. Down here, we're going to do the exact same thing. The only difference is we are now starting with oxygen. So the route that we take to get to those last couple steps, or that last step and a half, is going to differ a little, but those last step and a half are going to be the same. Now I go here. I see that there are 11 moles, balanced equation coefficients, 11 moles of O2 for every, again, 7 moles of CO2. And now it's exactly the same as what we did above. 1 mole of CO2 weighs 44.01 grams of CO2. All right. So the cool part about these is the limiting reactant problems, based on how we're doing them now, they have the same final like step and a half. All right. And that's important because the answers that we get in the end here are going to be the answers that we compare to one another. So I'm going to do both in the calculator here. I'm going to do the top one first. So that's 400 divided by 100.23 times 7, and then times 44.01. All right, and I get a massive number. 1,229.45 grams of carbon dioxide. That is the same thing with the oxygen. So 700 divided by 32 times 7, and then divided by 11. Again, you could just simplify, right? You can multiply the whole top, the whole bottom, get 2 numbers in the end. I like doing it all at once. It's completely up to you. And then I'm going to multiply by that 44.01 mass again. And look at that. I end up with 612.64 grams of CO2. So what is the significance of what we've done? Well, just like in our analogy with ice cream sundaes, let's say that the top is our ice cream, and the bottom, that oxygen, is our chocolate syrup. One of them is going to run out first, depending upon those amounts that we start with. And so we look at the product that both of them can make, and effectively we just look, hey, which one is the smallest, right? And it happens to be 612.64 grams. What that tells us is that based on these two starting values, we are limited to the amount of product that we can make, because one of them is going to run out first. And look, it's not always the one that we start off with less of, right? We started with less heptane, but we ended up seeing that the oxygen actually produced the least amount. So the oxygen produces the least amount. That means that our oxygen is the limiting reactant. It limited the amount of product that we could make, which means that this is our excess reactant, our heptane, all right? And what's cool about that is that gives us a couple of things. That gives us the limiting reactant, which we said is O2. And that also gives us this I'm going to say this theoretical amount of product that we should make, right? This value up here, that's just too much, because before we can even get to that amount of product, all the oxygen runs out, and now the heptane that's left over has nothing else to react with, so there's no more product that can be made. And I say this is the theoretical amount because this is what we would use in like a percent yield problem, right? Actual over theoretical times 100, right? And then you can plug that into the theoretical and so on and so forth. So, so that's pretty much what that tells us. And now the last thing to do would be, okay, well, now that I know that 400 grams of heptane is excess, right? There's too much of it. I'm not going to use all of it. Let's figure out how much we do use. So down here, what we can do is, because we know that oxygen is the limiting reactant, we can start with the limiting reactant, and we can figure out exactly how much of that heptane we're actually going to use, because we're not using all 400 grams. So let's see how much actually gets used with the 700 until it runs out. 32 grams of O2, 1 mole of O2, mole to mole ratio. In this case, it's 11 moles of O2 for every, remember, mole to mole ratio, we're talking about the two reactants here. It's 11 to 1, right? 1 mole of heptane, C7H16. And my last step, because I want mass, would be converting moles of heptane to mass of heptane, which we had as 100.23 grams of C7H16. All right. This is going to give us, whatever that might be, let's see, 700 divided by 32, divided by 11, and then times 100.23. We get 199.32 grams of C7H16. Now, again, what is the significance behind this? This is what actually reacts. So this is what actually reacts with our limiting reactant amount, all right? And you can see that's significantly less than 400, right? So once we react and all of that oxygen goes away, we can now figure out, hey, what's the amount of excess? Well, we started with 400 grams, right? This was our start. We only used 199.32 grams. So we can figure that out, what's left over, which is just 400, and pretty darn close to 200, huh? Minus 199.32. Yep, 200.68 grams of heptane, of the other reactant, the excess reactant, are left over. And that is that in a nutshell. So if you need any additional help, just let me know. Let Mr. Branch know, and then we'll rock and roll for the test. All right. See you later.